Hi, I'm Travis English from Kaiser's Engineering Group, and today we want to talk about Kaiser's schematic design review criteria for HVAC projects. Let's get the clicker right. So one of the problems we run into on HVAC projects is that Kaiser has a very different set of expectations around schematic design. Most design engineers doing the work have never really read the design contract. I'm not going to tell you to do that. But the word schematic design means something in industry. So typical architects and owners in HVAC design firms have expectations around schematic design, and Kaiser's expectations are quite different. And this hits HVAC engineers particularly hard. Now you can criticize Kaiser for this. Hey, it's idiotic to have schematic design requirements that are out of whack with the industry, or why don't you just align your SD expectations with everyone else's? That's a totally fair criticism. I'll even say that you're right. But we can't really change it, so here we are. This is where we are. I can't explain why. Kaiser projects get funded, and this is a very simplified timeline, but we get funded in two rounds of funding. We have scoping funding, and then we have full funding. So scoping funding is what we give a project at the very beginning, and with that, we hire a design team, we do investigations and assessment, and then we produce a schematic design package. Then we do an estimate of how much money it's going to take to complete the project. We put that estimate into an approval package and we ask for the rest of the money. So that's full funding. Full funding is the money we give a project to finish the project. And hopefully it's all the money that we give a project to finish the project. Nobody likes it when we have to go back for more money. So think of SD as that biggest time duration and the biggest technical lift of the design process. At the end of schematic design, the design is complete to a point where we can do an accurate cost estimate of the full funding costs. So DD and CD are really when we proceed with the design and finalize the design. So at the end of schematic design, the basis of design needs to be pretty darn complete. In particular, we need to have three things. First, all the equipment sizing needs to be done. There's no preliminary sizing. We need to know what the sizing is going to be. Then second, all the energy effects need to be known. If we're going to achieve energy savings on the project or not, then we need to know that, and we need to know how much. And then thirdly, all the associated issues need to be known and they need to be planned for. So we can't wait until DD to find out that the building has three-way valves that we're going to need to correct, or that there's duct leakage that we need to address, or that there's 7 zones with the cooling actuator out of whack, right? We need to know all that stuff in the SD estimate. And so my engineers, who I hope everyone watching this knows, Ben and Maya and Glenn and Sandy, when we're reviewing HVAC projects, we actually have an 18-item checklist that we check for in schematic design, and that is an awful lot. They're listed on this slide here. Well, I'm going to talk through each one of them in a minute here, but you may already be looking at this list going, oh my God, that's wrong. That's not what we do in schematic design. That's not what schematic design is, and that's why we're here. So let me jump right in. The first thing is a system description. And you could say that maybe this is just my engineers being lazy, but honestly, we are pretty spread out. We're spread out pretty thin. We're involved in a lot of different projects. So even if we reviewed your project last month, believe me, it's a blur. So just please provide a short narrative about the building and the project, details about the existing system and equipment, what is here, what's the condition, what are we doing, and why. Second is assessments. This is a huge item. We like to say internally, don't replace the engine on a car that has flat tires. And so in HVAC terms, what that means is if there's zone issues, air distribution issues, controls issues, valve issues, and we put in a brand new chiller, then we wind up with a brand new chiller serving all the same zone issues, air distribution issues, controls issues, and valve issues. So we did a pretty in-depth set of presentations on OPRs and assessments and data analytics last year. If you missed that, you can find all the links in the description of this video. Those are all still available on this channel, and please be familiar with that work. Third is existing capacity determination. So for any existing systems that you're working in, you need to basically ask two questions. What is the capacity of the system? And how do you know that that's the capacity of the system? The second question, obviously, is the harder one. You can say, hey, look, I looked at the old set of plans from 1995, and it says this is a 120-ton unit. Therefore, it's a 120-ton unit. Or you can look at the utility bills, do those heating degree day, cooling degree day, true ups, do the trending, look at the temperatures, and figure out what the capacity is. obviously we favor the latter. Number 4 is reliability. We have our Kaiser standard reliability requirements given in Chapter 23 of our design criteria. Please be familiar with those and align your projects to those. The note on this slide kind of says it. It says hint. We almost never have to tell an HVAC engineer to add reliability. I can't even think of a project where we've had to tell a mechanical engineer to add more equipment because they didn't meet the reliability standards. But I can give you 4 examples from the last 3 months where we had to tell mechanical engineers that they've oversized the reliability and they need to scale it back. So do be creative here. Use the natural system diversity. Not every system requires 100% backup, right? The 5th one is one that this is internal Kaiser language that we call the 3 R's. And this is very commonly missed. It is an internal Kaiser requirement of our plant maintenance program. But anytime we approach a piece of equipment, air handler, boiler, chiller, what have you, we are required to consider 3 cases: the repair case, the refurbish or retro commission case, and then the replacement case, the 3 R's. So it's very common for us to just see a project BOD that jumps to the 3rd R. It jumps to the replacement scenario. And we can't do that. We need to consider repairs and retro commissioning first. And sometimes you don't need new equipment. You need retro commissioning. The next one here is ventilation calculations. And yes, you are reading this correctly. We do want to see your ventilation calculations in schematic design. And yes, we do review those. Ventilation calculations are really important to system sizing and energy use. And I know that you think that you and your firm do them the right way, but we deal with 50 different firms. And let me assure you, if we asked all 50 firms to do the same set of ventilation calculations, we'd see a lot of different numbers. And so we have expectations around what those numbers should be and the ranges those numbers should be. If you submit a system that has 0.4 CFM a square foot of outside air, we are absolutely going to challenge you on that and want to have a conversation about that. This is one of those ones, the most common response we get to this is what we call a future tense response. That's where the engineer replies, yes, we're going to do ventilation calculations. We're going to do them during DD, or we're going to do them during CD. And we unfortunately, we just can't accept that. We need to see your ventilation calculations during SD, before that schematic design estimate. Right on the heels of that, again, you are reading this correctly. We want to see your load calculations in schematic design. Yes, the rooms might change later in DD or in CDs, and you'll need to update those calculations. Yeah, that's absolutely true. But the calculations need to be done in order to do the estimate, in order for us to have what we need for full funding. And also, if you are working in existing buildings, we want you to do load calculations. We do not assume that the previous design engineer who did a set of load calculations 10 or 15 years ago got it right, and that is still valid. So we require load calculations. That's why we call those contemporary load calculations. And we're not just looking at peak loads, we're looking at neutral conditions. We want to know what the range of the system is, and accuracy is important. Our data shows that a lot of load calculations have a high degree of error, and they result in oversized systems. We're going to talk quite a bit about that in a few slides. And so do check the results of your load calculations against the historical loads for those space types. So that's the first set of requirements. I'm not going to go through all 18 straight away. We have a little intermission here. So this is our intermission. And the best way to talk about this part of the conversation, which leads up to some of the other requirements, is as a question of ethics. Kaiser has a strong leadership commitment to environmental stewardship as a matter of human health. We are the first carbon neutral healthcare system. We've got some strong goals, and we're setting more on carbon, decarbonization, and energy. So we really have that commitment. So right around the time I got here, we started with this portfolio of just super high energy consuming hospitals and MOBs, lots of constant volume, inefficient systems running 24/7 in empty areas. And where we want to be 25 years from now is a portfolio of smart, low energy, efficient, net zero sites. And the only strategy we have to get from point A to point B is one project at a time. So our mantra is make every project an energy project. I put the old quote up there, attributed it to my dad. If it ain't broke, don't fix it. And the corollary to that is the important part here. If it is broken and you can see that it's broken, then you need to fix it. And you need to fix it when you see it. And we have a lot of broken energy systems on the HVAC side. The opportunity is huge. If you're doing an air handler or a boiler project in a Kaiser building, that could be the biggest opportunity that building sees in a 30-year period to become unbroken. So if you don't do that when you do an HVAC project, it's a missed opportunity. It's like you had your chance, you saw that it was broken, you were there, you had it in your power to do something, and you missed it. And we're seeing a lot of that. The bottom right corner here, there's some of these numbers are our M&V numbers, because we do look back at projects and we see what savings actually happened as a result of the projects. And right now, if you look at annual energy savings versus dollars invested, lighting projects have an energy savings return on investment that's 50% higher than HVAC projects. And to me, that's just wrong. It's sad. Because lighting energy is only 12% of our energy signature. HVAC energy is 75% of our energy signature. And we're doing 8 times as much investment in HVAC systems. And we're really just not getting energy savings out of those HVAC systems projects. So it is really, really just disappointing and something that we need to turn around. That being said, let's keep going down our checklist. The very next one being that we have subsystem energy targets. We published these a little over a year ago, and if you missed the presentation on them last year, please do familiarize yourself with that. It is a design requirement to assess the building systems you're working in against these targets, and it's a design requirement to do a gap analysis. So you don't need BAS systems or Clockworks to do this. If you have trends, that's great. But you can do it right off of the utility bills, and my engineers can always give you 3 years worth of utility bills for any meter. So you should always know whether the system you're working in is an energy rock star or an energy dog. And if you're working on an energy dog, we need you to be telling us how we can make that system better. Nowadays, usually before you start design, my engineers are running that 3-year historical utility report and putting it in the project. So if it's not already sitting there in eBuilder when you show up for work on the first day, then request it and we'll get that to you right away. You have to know where you stand in order to see where we're going to go with energy on a project. The next requirement is for load profiles. This goes back with the load calculations. We're never just looking for peak loads. We always want to see the profile. Where is that system operating in the neutral condition? And where is it operating? What is its most common operating conditions? Next one is maximum system sizing. This one can be controversial, but we've done a good amount of historical load analysis. If you're not familiar with those 3 videos on the right, please familiarize yourself with that work. We didn't just pick these numbers out of the sky. We've done quite a bit of work on the issue, right? HVAC systems have a lot of oversizing. Design engineers are usually not shocked by that statement. We all know, we're all pretty well aware that oversizing is an issue in the industry. So the real question is, how do you avoid oversizing? How do you do a load calculation that's defensible but avoids oversizing? The answer, the biggest thing that we found, is a lack of diversity in HVAC load calculations. HVAC load calculations tend to assume an occupancy and equipment profile, and then we place it in every room so it's happening in all those rooms at the same time. In reality, simultaneous loads are never the case, and so we can and we should be taking diversity, 40 or 50% on those space loads. And so if you submit a load calculation and you're above these numbers, you're above 0.7 CFM a square foot or above 20 BTU a square foot, then the first thing we're going to do is we're going to ask you about your room-to-room diversity assumptions and zone-to-zone diversity assumptions. For heating, we do have some climates. Well, we absolutely have climates where your calculations are going to be higher than that number, but be prepared to have a conversation about calibrating those also to historical loads. The typical just ASHRAE heating load calculation that we do overestimates actual loads by about double. And so we do always want to have a conversation about that heating sizing. The next one is VAV. I think, or I hope that we're done with the era of constant volume systems being acceptable. Prior to 2020, OSPOD used to require VAV boxes in every zone that you did VAV in, return air VAV boxes, I should say. But now that code has changed, and so we really want to do VAV anywhere and everywhere. Overnight turndown is part of VAV. That's a form of VAV. We almost always want to be doing that. Operating rooms need to have overnight turndown. So the only space in a hospital that really doesn't have VAV would be an airborne isolation room, and those are only about 1% of the footprint of the hospital, right, or less. VAV has been required by ASHRAE 90.1 for a lot of years. So in California, TOS 24 is actually quite behind on that. But it's been in our standards. It's been in Kaiser standards since 2017. And at this point, we've heard every possible excuse in the book for not doing VAV. And look, we get it. 90% of our hospital portfolio is constant volume. So every project comes up against the issue. And it goes, hey, I'm doing air handler number 2. Air handler number 1 and air handler number 3 are constant volume. So why don't I just make air handler number 2 constant volume and we'll just be on our way, right? Or you say, look, I'm doing the 5th floor and I noticed that the 4th floor and the 6th floor are just constant volume. So why don't I just make the 5th floor constant volume and we'll just be on our way? And the answer in both cases is no. We can't do constant volume systems because it's easier. So I, for one, have no intention of ever approving a constant volume design in a Kaiser building really ever again. So VAV is required. Maximum minimum heating sizing. This is a weird word for a weird concept, and it is particularly problematic. We did a white paper on this back in 2013, updated it in 17. For heating systems at low load condition, it's a recurring problem in the portfolio. Basically, the heating systems need to be able to turn down to a very low load condition. So 10 to 1 or 20 to 1 is not nearly enough. Really, if you read the paper, like in MOBs, you should be turning down to about 0.1 BTU per square foot. We check it at 0.5 BTU per square foot, so we'll reject your design if it can't turn down to 0.5 BTU per square foot. So make sure that you're addressing this. Then this kind of goes with the previous item, but it's the hydronic system BOD. We need to have that nailed down. So if you're going to do that turn down to 0.5 BTU per square foot, for a heating system in summer conditions, that means that your flow rate also needs to be able to turn down to that level. And that's a very small number. So we've seen in a lot of cases, if you simply count up the 3-way valves, that's way too much flow. And of course, this is not just heating. This is chilled water. This is condenser water. We need to look at minimum flow rates at equipment, any kind of variable primary flow configuration. Those minimum flows will kill your design intent. And for primary, secondary flow conditions, is it okay for the flow in the secondary loop to be less than the flow in the primary loop, as is often the case when you look at minimum flow rates of equipment, right? So all that has to be worked out in schematic design. The answers to those questions need to be worked out. Humidification calculations. If we're going to add humidifiers or not add humidifiers, we need to know that in schematic design. Please note that we do have this criteria around 450 hours per year. That's 5% of a year. So the idea here is that if you're going to place a humidifier in a zone that needs humidification less than 5% of the hours of the year, that humidifier is more likely to fail and cause problems than it is to humidify and cause humidity control on the rare occasion that it's asked to. So humidifiers are the single most failure-prone piece of equipment that we have by a good long shot. And so for that reason, we also don't allow them above ceiling spaces. We're always going to tell you to put them in the air handlers. Operating room conditions. This is just to make sure you know our OR design temperatures are different from ASHRAE 170. They're different from California code. This comes from an internal study we did on comfort and demand for temperature. So please just tell us in the BOD that you've read our design conditions for OR, and that you are in fact designing for them. Water quality assessment for evaporative systems. Anytime you're doing an evap-cooled HVAC unit or a cooling tower, our design criteria requires a water quality assessment. Kaiser standards. So there's details about those in the standards. We have a template posted. Existing buildings, this should be pretty easy. The source of the water is right there. For a new building, you have to find some sources nearby. You can get some information from the utility and then some sources nearby. If you're an HVAC design firm, you probably don't have a chemist on staff, so this typically requires an additional contract and some additional time. But any water treatment plans that you have need to be based on water quality. It sounds so obvious when you say it out loud, right? Any water treatment plans that you have need to be based on water quality. but yet 90% of the time, we wind up making this comment. Duct leakage and duct sealing. Remember that leakage is wasted fan energy. In our assessment requirements, we expect the design team to provide the test for existing ductwork for leakage. And then we need to look at repair or replacements of sections or what the strategy is to reduce leakage. We're targeting leakage around 5%. That's generally where it's sort of in with the ASHRAE guidelines. So leakage rates of 20% are not acceptable. And we don't want you designing bigger fans around big leakage numbers, right? There are some cost-effective options, particularly in the last 5 years, that have sprung up to address duct leakage, and we've had some success with those. But that scope absolutely needs to be in your schematic design estimate. We can't find out about that later during the design phase of the project. And then finally, life cycle cost. The culmination of our schematic design effort is our life cycle cost analysis. Not every project requires a life cycle cost analysis. If you've been through the 3 Rs and you have multiple systems on the table that have different operating or energy costs, that's when life cycle cost analysis comes into play. Please remember that the margin of error on energy calculations or energy modeling is not 0. We have our life cycle cost parameters white paper, and it talks about that rounding for a calibrated energy model. We accept 10% rounding. Otherwise, it's 15%. So if you have 3 options and the energy use of all 3 options are within 10%, then you can quickly summarize that life cycle cost, and it is really at that point a first cost analysis. Kind of similarly for operating costs, we really only want to look at operating cost differences that are bona fide and significant. A good way to think about that is, unless you have to hire an additional person or could hire one less person, then you're probably not talking about an operating cost difference that's bona fide or significant. And so very often you include those as the same on all your scenarios. And then just to make sure that we say it, HVAC engineers are not cost estimators. So if you're an HVAC consultant, you should categorically never be providing first cost data. We have estimators that do cost estimating 40 hours a week. That is literally what they do for a living, so do not do it. Okay, so just to sort of wrap up, once again, Kaiser projects get funded in 2 rounds of funding. We have our scoping funds, and then we have our full funding. So at the end of schematic design, our design needs to be complete to a point that we can do an accurate cost estimate of the full funding costs. And in particular, all the equipment sizing needs to be done, all of the energy efficiency or energy effects need to be known, and then all of the associated issues need to be known down within the system, whether that's duct leakage or 3-way valves. That all needs to be planned for at the end of schematic design. That's why we do a very intense review of schematic design, and that's why Kaiser SD is what it is. So I think if you're watching this video, you probably know where to find me or where to find our engineers. Please let us know if you've got any questions, and project-specific questions, always welcome. Thanks.